Hello and welcome again. So this is our lecture number 4, okay? And this lecture is in continuation of our previous discussion on Poisson's equation, okay? So last time we discussed Poisson's equation and we wrote del square V equals to minus rho over epsilon naught. So this was our Poisson's equation, which relates the double derivative of potential with the local charge density, okay? So what we're going to do today is to study this equation in three symmetries. So one is the Cartesian symmetry. The second one is the spherical symmetry, and the third one is the cylindrical symmetry. Cylindrical symmetry. Maybe I will leave this one for homework, okay? Or we can discuss the cylindrical symmetry in the next video lecture, okay? But today we are going to do Cartesian symmetry and the spherical symmetry problems regarding the Poisson's equation, okay? So let's start. Now, before starting the problems, what I will make my condition. The condition will be that rho is equals to 0, okay? So that we can solve our problems very easily, okay? So this is our condition and I am taking the Cartesian system first, okay? This is my first problem, okay? So if rho equals to 0, then my Poisson's equation will become del square V equals to 0. Now in the previous lecture, I have already told you that the trivial solution equals to V equals to V naught, where V naught is a constant. It's a trivial solution, okay? But today what we are going to do is to solve it for some boundary conditions, okay? So today we'll introduce some boundary conditions also, boundary conditions. So this was the trivial solution, okay? Now for this equation, we know how to solve it in Cartesian system because we know del square in Cartesian system is, so let me write, del square in Cartesian system is simply dou square by dou x square plus dou square by dou y square plus dou square by dou z square, okay? Now what I will do, I will simply write my Poisson's equation as dou square by dou x square, okay, plus dou square b by dou y square plus dou square b by dou z square equals to 0. So this is my Poisson's equation in Cartesian system. Now one more assumption that I will make so that I can make our life easy. So that is the potential depends only on x, okay? That is v of xyz is actually v of x only. So by that, what I'll get, this term and this term will cancel out, okay? So I can simply write, and if this is the case, that potential only depends on x, then I can rewrite my partial differential into simple differential. That is d square v by dx square equals to 0. Okay. Now, what is the solution of this equation? This is a second order differential equation. Its solution is simply given by v of x equals to ax plus b. It's a linear. Okay. All right. Now, what I will do, so this is a solution, but I have two constants here. So I have this constant here and this is the second constant, which depends upon the problem, okay? Now let's take a problem, okay? The simple problem I will take is a um, capacitor problem, okay? So this is the simple problem, capacitor problem. So I want to use the Poisson's equation to calculate my potential, okay? And this is my solution because I know if I have the Cartesian symmetry, then this will be the solution, okay? I will use this solution for capacitor problem. Now, suppose I have two infinitely long parallel plates. Okay, so suppose this is at x equals to 0, and this one is at x equals to suppose d. Okay, and this one is potential 0, and this one is potential v naught. Okay, and the difference between these two plates, potential difference is v naught. Okay, and this is my suppose x-axis. Okay, this is my x-axis. Now, in this region, in the region between the plates, suppose this region, there are no charges. If there are no charges, that means rho equals to 0. Rho equals to 0, okay, between the parallel plates. So rho equals to 0, that means I can use Poisson's equation for this case, del square v equals to 0. And I know the solution for this equation, okay? So that's simply ax plus b. So the solution will be simply, v of x equals to ax plus b. So I solved the potential problem, capacitor potential problem using Poisson's equation. The only thing remaining is to find the constants, okay? So these two constants, that's all that I have to find, okay? Now let's find the constants and b. So for that I will use boundary conditions, okay? Now when x equals to 0, potential equals to, we know potential equals to 0. So if I substitute these two variables in this equation, what I will get 0 equals to a times x equals to 0 plus b. So this will give me b equals to 0, right? So b equals to 0. Now what about the second constant? So for that, I will use the second boundary condition. That is when x equals to d, v equals to v naught. Okay, this is my second boundary condition. So when x equals to d, potential is v naught. So that implies if I substitute these two into this equation, that then I will get v naught equals to a times x equals to d plus b we know is 0. So okay, it's simply 0. So from this we'll get the second constant a, that will become simply v naught by d. So now we have both two constants and we can put it into our equation to get the final solution. So the final solution will be v of x equals to a के बदले v naught by d times x plus 0. Okay, so this is my potential in case of a parallel plate capacitor. Okay, so that means if I have a parallel plate capacitor with potential difference v naught between the upper plate and the lower plate, this will be the solution. Okay, right? And if we know the potential, we can find the electric field simply by taking the gradient with respect to x-axis, suppose. So that will be minus dv by dx. That will become minus v naught by d. Okay, it's constant, as we already know that in the capacitors, electric field inside the plates is constant, but the potential varies linearly. Okay, so if we have any system where there is a symmetry, so this will be the solution, and depending upon the boundary conditions, we just have to find a and b. Okay, so v of x equals to ax plus b is a general solution for a Cartesian symmetry problem. Okay, but remember, this I did for when v of x y z was depending only on v of x. That means there was only one dependent variable x, so there was no dependency on y or z. It gets complicated if v of x y z has y dependence as well as z dependence, so it will get complicated. So but we'll not go into those complicated problems. Okay, so this is done now. So we can have many problems related to this Cartesian symmetry, but this is enough. Now let's go to spherical problem. Spherical symmetry problem. Okay, and our master equation is del square v equals to minus rho over epsilon naught, and we have the condition that rho equals to 0. So del square v equals to 0. But because we are working in the spherical system, we have to use the Laplacian operator in spherical coordinates. As we know that the let me write here, the del square operator in spherical system is given as, so it's very long equation. So del square equals to 1 over r square dou by dou r of r square dou by dou r plus 1 over r square sine theta dou by dou theta of sine theta and dou by dou theta. Okay, and there is one more term plus 1 over r square sine square theta dou square by dou phi square. Okay, so what I have to do now is to solve this Poisson's equation. Actually, it's not called a Poisson's equation when rho equals to 0. It's called a Laplacian equation when. Okay, so this is the Poisson's equation, but its special case is called a Laplacian equation. So I have to solve this for spherical symmetry problems. So this is what I have to use for del square. All right. Now, again, in the previous case when I said that potential depends on x only, here I will again use the assumption that the potential depends on r only. Okay, potential is a function of r radial distance only, so it has no dependence on theta and no dependence on phi. Okay, so no dependence on these two variables. So if there is no dependence, then this term will not be there and this term will not be there. So my Laplacian operator will simply be 1 over r square dou by dou r of r square dou by dou r of v equal to 0. Okay, I just wrote dou square v equal to 0. Okay, so this is my Laplacian equation when the potential depends only on radial distance. Okay, now you can simplify this a bit. So 1 over r square can be put even to this side, so it becomes simply, and also you can do one more thing, you can remove this partial with simply d. Okay, so it becomes d by dr of r square d by dr equal to 0. Now you know the solution for this equation. Okay, I'm not going into the solution. Okay, you can do two integrations and you can find the solution for this equation. I'm not going to find the solution for this partial differential equation. Okay, sorry, differential equation. So its solution, if you can find, here we have v. So v will be equals to a by r plus b. Again, we have two constants a and b because it's a second order differential equation. So second order differential equation will have two constants. Okay, so it's again homework for you. You just have to do integration. Okay, do integration and you'll find that the solution will look like this. Okay, again you have two constants. Now depending upon the problem, you have to find these two constants to get your final solution. Okay, now let's take an example. Suppose my example is like this. Suppose I have a spherical charged shell at potential V equals to V naught. Okay, of radius r. Okay, and I want to find what is the potential. Okay, outside as well as inside, outside as well as inside. So this I want to find the potential, but I know how the potential will look like. Potential will have this form. Okay, so this I already know because there is no charge. So there is no charge inside, no charge inside, and no charge outside. So I can use Laplace's equation for rho equal to 0. So so this is the equation I know. I just have to find the constants. Now let's find for the outside case. Okay, outside case. For outside case, we know V will be equals to A by R plus B. Now I just have to find two constants. For that, I will use boundary conditions. The boundary condition is that when R equals to R, what will be the potential? Potential equals to V naught, right? So any point on this spherical shell will have the potential V naught. So that will give me when V equals to V naught. So I just have to put these two uh, conditions into this equation. So that will give me V naught equals to A by R plus. mm, let me use a different boundary condition first so that I can remove this B. Okay, so that I can remove this B. Let me use like this. When R equals to infinity, when R equals to infinity, we know when R equals to infinity, every field becomes 0. So V will be equals to 0. So in that case, V equals to 0 equals to A by infinity plus B. Now A by infinity will become 0. So this will give me B equals to 0. Okay, so I got the first constant, that is B equals to 0. So let me rub this. So B equals to 0. Now I need to find A. So for that I will use this boundary condition, that is when R equals to capital R, the potential equals to V naught. So V naught, so substituting these into this equation, V naught equals to R, capital R is small r plus B is 0. So it implies my constant R will be equals to R times V naught, right? So R times V naught. Sorry, I did a mistake. So here, so first constant B equals to 0 when R equals to capital R. So V naught equals to A by capital R. Okay, plus 0. So it implies A equals to V naught capital R. So this is my second constant. So I have both these two constant. Then my solution will be final solution V equals to. So instead of A, I will write V naught capital R by small r plus B is 0. So I won't write that. So this is my solution for a spherical uh, shell having potential V equals to V naught. But remember, it's for outside. Okay, so outside. So if this is R, when there is capital R, then outside this R it goes as 1 over R. Okay, and this is V naught. But what about inside? Now the question arises: what about the inside? Okay, so if you look inside, so R will become 0. If R becomes 0, V will tend to infinity. Okay, we will reach infinity. Okay, so this equation breaks down when R equals to 0. So instead, what will we do? So to find the potential inside this spherical shell, we will just guess the solution. Suppose V equals to V naught. Okay, I'm just guessing the solution. It's just my guess. Okay, if this is my solution, it has to satisfy this equation. It has to satisfy this equation, Poisson's equation. That is this equation. Suppose, right? Does V equals to V naught satisfy this equation? Yes, of course, because if I take the gradient differentiation with respect to R, it becomes 0. And does it satisfy the boundary conditions? Yes. At V equals to V naught, it's this solution satisfies. So my guess is the only solution because I'm using the uniqueness theorem. If my guess satisfies the Poisson's equation as well as the boundary condition, then it is the solution. So यही solution है inside के case. So V equals to V naught. Okay. Now the next case will be the spherical cylindrical symmetry. So that will take for the next video.